G'day! Here's a cute probability puzzle. It goes as follows. I'm going to start with a 5 by 5 array of dots, 25 dots, and I'll colour them red and green. In fact, I'll draw all the dots on the main diagonal, all 5 dots on this main diagonal, I'll make them green. But then I'll make all the dots on the lower portion green as well. So there's another 4 green dots there, 3 more green dots, 2 more green dots, and 1 final green dot. And I'll make the rest of them on the upper portion red. So that means I've got 4 red dots along here, and 3 along there, 2 and 1. Alright, so I've coloured the dots red and green. And here's the question. So suppose I choose 2 dots out from this diagram. So pull one dot up, pull a second dot. So choose 2 distinct dots. Pull a dot, pull a dot. What are the chances the dots I'm holding in my hands are different colours? Choose 2 distinct dots at random. What are the chances I've got dots of different colours? Alright, so that's the question. And I'm actually going to work it right now. I'm going to show you how my brain works. So let's see, so what have we got going on here? We've got 25 dots. I guess I need some numbers. For example, 5 plus 4 plus 3 plus 2 plus 1. The number of green dots is 15, and the number of red dots must be the remaining 10 to get 25. So that's telling you what's happening here. Alright, so how do I think of probability? I imagine doing the experiment, say, 1 billion times, some large number of times, and imagine having a table of all the outcomes that occurred. So imagine, here's my hypothetical table of all the outcomes that occurred when doing this experiment 1 billion times. But I can see from these numbers, that 15 out of 25, 15 25ths of the time, I'm going to first choose a green dot. So 15 25ths of this data is going to have a green dot appearing first. And 10 25ths of the data will have a red dot appearing first. Okay, so my table, whatever it is going to have 15 25ths of it will be beginning with green, and 10 25ths of it will be beginning with red in this idealized way of thinking about the probability. Alright, so if I did choose a green dot first, that means I pulled out a green dot. That means I'll have 14 green dots left and still have 10 red dots. Whereas if I chose a red dot first, pull it out, number of green dots stays at 15, but the number of red dots is 1 less. It's now 9. Alright, but now think about this portion of the data, just where all the data began with a green dot. Because I know I'm going to do a second dot coming out, and I can see, from here, from these figures, 14 24ths of the time, 14 24ths of the time, the second dot I pulled out will be green. And 10 24ths of the time, the second dot I pulled out, first dot's green here, is going to be red. Okay, now look at this data of all the cases where I hadn't have a red dot first. I can see from these numbers, I can see that 15 out of 24 times, my second dot will be green, whereas 9 out of 24 times, first dot was red, but my second dot would be red 9 24ths of the time, amongst that part of the table. And that's all I need for my table, was doing the experiment. Pull out a dot, pull out a dot. I've got it there. There's all the possible outcomes, and all these figures here telling what proportions of each outcome I'm seeing in this data table. Grand! Now what I want to see, I want to see 2 dots, different colors. I want to see either green, red dot, that'll be fine, green, red, grand. Or I want to see red, green, that'll be fine, red, green, also grand. I don't want to see green, green, I don't want to see red, red. So the question is, what proportion of this table is actually what I want to see, namely what I've shaded here. Well, I've got all the proportions on the sides written out. I can actually work that out. So the probability of seeing 2 different colors, P diff, so I'll write P diff, I'm going to just write the D neatly. The probability of seeing 2 different colors will be this proportion of the time plus that proportion of the time. This whole proportion of the table, that's actually shaded. So let's work it out. This is 10 24ths of 15 25ths of the table. 10 24ths of 15 25ths of the table. So it's 10 24ths times 15 25ths of the table. Plus I want this proportion here, which is 15 24ths of 10 25ths of the table. 15 24ths of 10 25ths of the table. Alright, so that's it. That's the answer. Can I make that look friendlier? So I'm going to get rid of this, so I need some more space. Let's see. The numerator is the same in each case. The denominator is the same in each case. This is actually, there's actually 2 copies of 10 times 15 on the top and 24 times 25 on the bottom. Okay, can I make this look simpler still? Let's see. Okay, so there's a 5 in there and there's a 5 in there. So this 10 is really 2 times 5, and this 15 is really 3 times 5. So I see 25 on the top and 25 on the bottom. No need to worry about those. I'm left with a 2 times 2 times 3 on the top. That's 12 over 24. 12 over 24 is 1/2. Whoa! choose a dot from here and a second dot from here, choose two distinct dots from this table, from this picture right here, and you will have a 50% chance of seeing different colors. Wow. Okay, here's the exciting thing. The size of the square doesn't matter. Check it out. Suppose I started with a 4x4 array of dots. Did the main diagonal green, then the lower half green, upper half green is red as well. The chance of choosing two distinct dots of different colors here is 50%, 1/2. Do it for a 3x3 table. The chance of choosing two dots of two distinct different colors, 1/2. Do it for a 1,000,000 by 1,000,000 table. Whoa, I'm not going to draw it. But it would be a table with greens all the way down there and all the lower half. Reds everywhere else. There'll be red and red. Guess what the chance of choosing two distinct colors is? It's 1/2. No matter the size of the table, the chance of choosing two dots of different colors is always going to be 50%. Whoa, whoa. So I'll actually show that in the next part of the video, but if you want to pause right now and try that for yourself, like can you explain why that's the case no matter the size of the table, go for it. Or just hang on, because I'm about to go for it too. See you in a moment. Okay, let me spend a moment talking about one of my favorite sequences in mathematics, that of the triangular numbers. 1, 3, 6, 10, 15, 21, 28, 36, and so on and so on. These are the counts of pebbles you have in your hand that you can actually make into beautiful triangular arrangements. For example, with 10 pebbles, I can make this pattern of 1 dot, 2 dot, 3 dots, 4 dots, that lovely triangle of dots. With 6 pebbles, I can make 1 dot, 2 dots, 3 dots, and so on. I can see these beautiful triangular arrangements. In fact, I can think of this triangular number here as literally 1 dot plus 2 dots plus 3 dots. And this one is 1 dot plus 2 dots plus 3 plus 4 dots. This one is 1 plus 2 plus 3 plus 4 plus 5. This one is just as 1 plus 2. And this is not much of a triangle, but it seems to make sense to actually include it in this list. Beautiful, there it is. There are the triangular numbers. So the kth triangular number, I'll call that TK, is actually the sum of the first k counting numbers. Great. Now that's a bit of an awkward formula, but there's actually an easy way to get to a lovely way to see that formula in sort of a closed form. And actually the pictures I was drawing earlier is the key to that. But let me go back and draw that 5x5 array of dots, because actually that was really two triangular numbers combined. So here's 25 dots again, and I had, let's see, green was the main diagonal and lower. So 1 dot and 2 dots and 3 dots and 4 dots and 5 dots. So there's actually the fifth triangular number right there. And the red ones were really 1 dot plus 2 dots plus 3 dots plus 4 dots. That's the fourth triangular number. So this picture here is telling me that the fourth triangular number compared with the fifth triangular number gives me a square number, 5 squared. Which makes sense. 10 plus 15 is 25. There it is. In fact, there's nothing special about the dimensions of this particular picture. I can see that any two consecutive triangular numbers must combine this way to make a perfect square. And look, 1 plus 3, combine them, you get 4, a square number. 3 plus 6, 9, a square number. 6 plus 10, 16, square. 25, square. 15 and 21 adds up to 36, it's square. There it is. Now, actually, to get to the issue at hand though, however, it's a little bit awkward. I've got two different triangular numbers here. I could actually add to this picture this clever way. Let me put one more column in, one more column of pinks. So I'll do one more column of pinks. So now I'm going to make this a column of 1 pink and 2 pinks and 3 pinks and 4 pinks, and now it's 5 pinks. Now it's the fifth triangular number. So now what I'm actually seeing here is that 2 copies of the fifth triangular number. So 2 copies of the fifth triangular number is really, well, it's not square anymore. It's actually 5 still, but I did 5 plus 1 more. It's really 5 by 6. It's now 5 by 6. Which means, oh, the fifth triangular number all by itself must be 5 times 6 divided by 2. 30 divided by 2 is indeed 15. There it is. But actually, there's nothing specific about this picture. I can measure the scales any way I like, because I can see if I did k dots this way, and it did k dots here along here as well, but then added one more column to make this actually a k by k plus 1 rectangle, then I'd see that 2 copies of the kth triangular number would actually fit together like this to tell me that 2 copies of tk is actually k by k plus 1. K by k plus 1, in which case, oh, divided by 2, the kth triangular number is actually k times k plus 1, all divided by 2. If you want, you can write the top line as k squared plus k if you like, and then divide that by 2, all good and grand. But there's a nice closed formula for the kth triangular number. Great. All right, okay, but let me go back to what I was asking in the previous video, which is, well, go back to 5 by 5, get rid of that extra column. So let's make this K by K now. So even though I've got on the board here the 5 by 5 picture, literally, think of this as the K by K picture, where I've really got the number of greens is actually the kth triangular number, and the number of reds here is actually the triangle number just before that, the K minus 1th. I wonder, can I work out the probability if I choose two distinct dots at random that I'm going to have two dots of different colors in my hand? Is it a half? Is it always a half, no matter what K is? Well, the answer is yes. Let's see it. Let's see it. So let me just write this up here out the way. So the kth triangular number is actually K times K plus 1 divided by 2. And I'm going to now use this space. All right, here goes. Let's work it out. Now, I'm imagining in my mind that table of data I had, where I had the portion where I chose a green and a red, and the portion I chose a red and a green. That's how I got two different colors. So I'm going to do that same mentality right now, but in a sort of abstract sense. So the probability of choosing two different colors will be the two different ways that could happen. The first way was the probability of choosing green first, then red, plus the probability of choosing the other way around. It was red first, then green, then green. Okay, terrible handwriting, but green first, red second, then add to that the proportion of times you get red first, then green. All right, okay. Proportion of times I choose green first will be, well, there's this many green dots, TK out of the total sum of dots. What's the total sum of dots? K by K out of K squared. The chances I'll choose green first is this, and then follow that by choosing a red. Well, okay, there'll be one less green now. So the number of dots I'm working with is K squared minus 1, one less of them, but I still have TK minus 1. The chance of choosing a red dot out of the remaining dots is TK minus 1 out of K squared. So there's an abstract formula for choosing green first and then red. Whew. And then, the other way around, probably choosing red first. Okay, back to the visual diagram. Starting out, choosing red first will be this many, TK minus 1 out of all of them, K squared. One of the red dots is gone. So now I've got K squared minus 1 dots left. And now I want to choose green second, and that count hasn't changed. I've still got that many, must be TK out of K squared minus 1. Right, so the probability I seek then is given by that ghastly looking formula. But if you look at it, the numerator is identical, the denominator is identical. These are two copies of the same fraction. This is really twice TK minus 1 all over K squared times K squared minus 1. All right, so can we unravel that? Okay, I'm running out of room here, but let me get rid of this now. I don't think I need that anymore. This is just now an algebra game. I'm crossing my fingers that this all just magically ends up being a half. So let's see it, let's do it. Okay, this equals. Okay, let's use our formula. TK is the K times 1 more all divided by 2. So this is twice K times 1 more all divided by 2 times the K minus 1th will be, okay, the K minus 1th plus 1 more divided by 2. K minus 1th times 1 more is just K all divided by 2. All that is over K squared, okay, I'm going to be sneaky. K squared minus 1. I see a K plus 1, K minus 1. Difference of two squares. The reason I do that is I'm seeing lots of similar stuff going on. What I've got at the top, I've got 2's cancelled there. This half survives on top. So I've really got a half times K plus 1, K minus 1, K all over K squared, K plus 1, K minus 1. Cancel, equals 1/2. Irrespective of the size, square I'm playing with, the probability of choosing two dots of being distinct colors is actually 1/2 every single time. Beautiful, 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 beautiful. But then comes the interesting part. Dick Hess of MoMath a few years ago asked the converse. Does this work backwards? Now things start to get really interesting. Suppose I give you some count of dots that are green, some count of dots are red, and I tell you the probability that the two dots you choose are going to be different colors is 1/2. What can you say about the original counts of dots? Must they be triangular numbers again? Whoa, let's explore that next. Okay, so here's the clever question from Dick Hess of the National Museum of Mathematics. Can we do this backwards? Suppose a bag contains some green and red balls. We don't know how many of each, but we do know the counts of these balls are such that if you were to pull out two balls from that bag, the probability of seeing two different colors in your hands is 1/2. we got the answer. And the question is, well, can we say anything about the setup and how many green balls and how many red balls there must have been in there in the first place to make that happen? It's a great question. It's a really good question. So let's see if we can answer it. Let's see if we can analyze this. We don't know the number of green, we don't know the number of red balls, but let's say the number of green balls is, say, G for green, and the number of red balls is R for red. Okay, that seems good notation there. Okay, that many greens, that many reds, that means the total number of balls in the bag is G plus R. And we're told that the probability of seeing different colors if you were to pull out 2 balls at random from the bag is 1/2. All right, okay. And we know how to work out that probability. We've done it twice actually already. Let's do it a third time in this setting. So the way to get balls of different colors, either pull out a green one first, then a red one, or pull out a red one, then a green one. So pull out a green one first. Chance of that is selecting a green one out of all G plus R of them, followed by then selecting a red one. R red balls out of what's left, G plus R minus 1. Green then red, given by that. Or we can actually select a red one first, R out of the G plus R balls in the bag, and then follow that by selecting a green one. There's G of them out of 1 less, G plus R minus 1. Okay, so there's the probability of selecting 2 balls of different colors equals 1/2. Again, okay, we see those 2 fractions are identical. So this is actually really 2 GRs over G plus R times G plus R minus 1. And we want that to equal 1/2. That has to equal 1/2. Okay. Might as well get rid of all this. That's what the equation is boiling down to, except it's fractional. I don't like the fraction stuff. Let's actually multiply both sides by 2, remove that half, and multiply both sides by that denominator, bring it up over yonder. So really, this is actually 4GR. 4GR equals G plus R times G plus R minus 1. Okay, all right, I'm still just playing with the algebra, not doing anything deep here. I guess I'll keep playing with the algebra, expand this out. This is really G plus R times G plus R. So it's G plus R squared minus, G plus R times minus 1. So minus a G plus R. So this is really 4GR equals G plus R squared, G squared plus 2GR plus R squared, then minus a G plus R, minus a G minus an R. All right. All right, still just flailing around here. Okay, let's bring this negative stuff over yonder and subtract 4GR from both sides. So this is going to say, this really says G plus R equals a G squared minus 2GR plus an R squared, and that's it. And that's nice. That's really nice. This is saying G plus R equals G minus R squared. Beautiful, beautiful. Okay, all right, that looks much simpler. That looks friendlier. Actually, you know what? It's actually saying something really curious. This is the total number of balls in the bag. We must be in a setup where the total number of balls in the bag is a square number. And in fact, it's the difference of the counts of the 2 colors squared. I mean, that feels very special. That seems awfully special. Okay, so what else is this telling me? It must be telling more stuff. Oh, this could either be G minus R or R minus G. This could go either way because of that squaring. So am I assuming there's more green balls than red or the other way around? Oh, actually, first of all, I should ask this. Could G equal R? Could I have the same count of balls in this setup? Well, actually, I think this equation is telling me no, G won't equal R, because if G equals R, this tells me that 2 G's, G plus another G, would equal 0. Oh, no green balls, no red balls, not true of anything. All right, so yes, okay, the count of green and reds must be different. One's larger than the other. So there could be more green balls than reds, or could be more red balls than green. But they're just names of colors. Actually, the names of the colors doesn't matter. So we might as well just assume we're in one of those situations. Let's assume that G is bigger than R, and I guess working with G minus R makes sense. All right, okay. All right, but now I'm going to actually think about this equation. What's it really saying? How can I find actual values for G and R that fit that? All right, okay. I'm going to do something really, really sneaky. G plus R equals something. G plus R equals this, G minus R squared. I'm seeing G minus R. Wouldn't it be lovely if I knew what G minus R equals as well? Because then I have a formula for that. Because that will give me a pair of equations that I know how to solve. In fact, it's a very simple system of equations right there. And in fact, you know what? I'm going to be really, really sneaky. I do have a formula for G minus R. It's the most obvious formula for G minus R. G minus R happens to equal G minus R. I mean, that's just true by default. That's going to always be true. So actually solving this system of equations, solving this pair of linear equations, well, not linear, pair of equations, is actually just, well, since that's always true, is equivalent to solving that first equation on its own. All right, but the reason I like that, because I really know how to handle that. If I add these two equations, it tells me I'll get a g plus a g plus an r plus a negative r. I'll just get 2g's equals a g minus r squared plus a g minus r. Which means that divided everything by 2, g is something squared plus the something divided by 2. That's very nice. To get to the r, don't add the equations, subtract them. Top line, take away the bottom line. G's will cancel, and r, take away negative r, would give me 2r's. Equals this one, g minus r squared, take away g minus r. To get r by itself, all by itself, divide everything by 2. Beautiful. So I actually get r as some number squared minus that number divided by 2. In fact, I might as well give this difference number a name. Let me call it k. K is going to be g minus r. So this number of green balls is actually k squared plus k divided by 2. It equals k times k plus 1 divided by 2. It's actually the kth triangular number. G is the kth triangular number. Whoa. And r is actually the same k squared minus a k over 2. That's really k times k minus 1 over 2. That is the formula for the previous triangular number. R and G must indeed be consecutive triangular numbers. Just like we had in the very beginning of the video, that's the only case this is going to happen when I've got consecutive triangular numbers. That does it. That's amazing. So actually, the only solutions to this problem, the only counts of balls you can have in this bag, G and R, must be consecutive triangular numbers. So we're going with G bigger than R in this setup, so you can have 3 and 1. Or you have the next triangular number 6 and the one before it 3. Or the next one 10 and the one before it 6. Or 15 and 10. Or 21 and 15. Or 28 and 21, and so on and so on and so on. These are all the solutions to the original problem, both forwards and backwards. Whoa, this characterizes the triangular numbers in some sense. That's amazing, wonderful. So that actually feels like a complete little set of videos we've just done right now. But you know what? We can keep going if we want to, because what seems irresistible right now is to start playing with that 1/2. Well, if I change that to another fraction, in fact, the simplest fraction my brain can think of is 1/3. Well, if we change the question, trying to work backwards from that fraction instead, what sort of solutions will we get then? Something like the triangular numbers? Something different? Who knows? We should explore that. It's going to be a lot of fun. But you know what? The math starts getting deeper and deeper and deeper the more we play with this sort of question. You've got to love it. So if you're game for it, we can just keep on going. So let's do it. Let's keep on going. Okay, let's now play with the variation. The probability of choosing 2 balls coming out of the bag being different colors is now 1/3. Given that, what can we say about the count of green balls and count of red balls that must have been in that bag? Well, we can say that must be true. Here's the probability of choosing two balls of different colors, and that process now has to equal 1/3. So the question is, what does the equation say about the values of G and R? What values of G and R make that true? All right, so I guess we have to play with that equation. So as before, I can see it's really just 2 copies of the same fraction. So 2GRs over G plus R minus 1 is 1/3. I, like everyone else, don't like working with fractions, so let me multiply both sides by 3 and both sides by that denominator. So 6GRs equals G plus R. Well, it's going to be G plus R squared minus a G plus R. Oh, actually, why did I do that? Why did I do that? My brain wanted to do that, keep this sort of structure here. Oh, okay, I'm going to be really explicit. I liked my G plus R's and my G minus R's last time. In fact, let me let alpha be G plus R and my beta be G minus R. Because I have a feeling they played a key role in the previous section of the video. I'm going to see if I can use their structure right here, because I've got alpha squared minus alpha right there. That seems too nice to me. That's a bit annoying. There's a single G and a single R, but I can use these equations. If I add them, I'll get that 2G's equals alpha plus beta. So I know that G is actually alpha plus beta over 2, and subtract them, I get that R is actually alpha minus beta over 2. Am I right? R take away negative R. Yes, 2 R's. Beautiful. So maybe I should put alpha and beta into that equation. But I will do that. So I just realized I'm a little bit nervous about what I'm just doing, because G minus R. Am I assuming G is bigger than R again right there? Could these be equal? Could G equal R? Okay, so side note. So here's a really bad bought technique. Could G equal R? In which case, I might be in trouble doing this work. If G equals R, what's going on? Then this would be saying that 6G squared equals 2G's squared, so it's 4G squared minus 2G. So 2G squared will equal to negative 2G's. Divide both sides by 2 by G, assuming G is not 0, then I get that. Oh, I get that G is negative 1. Well, that's even worse than G being 0. All right, no way. G, I know, has to be at least some positive numbers. Not going to be negative 1s, not going to be 0. G won't be equal to R. All right, so again, either there's more green balls than red or other way around. That's just names of colors. I might as well just assume that G is bigger than R. So we'll assume that G is bigger than R and they're both at least 1. Okay, good. All right, so that means doing this might be okay. That's a positive integer. That's a positive integer. We're good. We're good. So the equation I'm really playing with then is 6GRs equals alpha squared minus alpha. Yep. So 6G's alpha plus beta over 2 times R alpha minus beta over 2 is alpha squared minus alpha. Uh-oh, pen's going to start running out. See how fast I can get through this. All right, 6 over 4 and a difference of 2 squares. So that's really 6 over 4. That's really 3 over 2. 3/2 of alpha squared minus beta squared equals alpha squared minus alpha. Aha, aha. Okay, pens don't run out on me at this stage. I'm getting excited. I'll keep the original equation on there just in case. That's helpful. All right, but what I've got right now is, let's multiply both sides by 2. So I've got 3 alpha squareds minus 3 beta squareds equals 2 alpha squareds minus 2 alphas. I think I did that correctly. So alpha squared minus, alpha squared plus 2 alphas equals 3 beta squared. Okay. Oh, I think I want to add 1. That seems too irresistible. Let me add 1 there and add 1. So this is really saying that alpha plus 1 squared equals 3 beta squared plus 1. All right, all right. I'm okay. I kind of like that because this is something very famous in mathematics. In fact, I've already introduced alpha and betas. Let me now let A be alpha plus 1 and let B be beta. Because this is now telling me the equation I'm really playing with is A squared minus 3B squared minus 3B squared equals 1. I've actually converted this equation here to what's a very famous equation in mathematics. Very famous equation. This is known as an example of PELL'S equation. PELL'S equation. I'll talk about who Pell is and why his name got attached to that in a moment. But mathematicians have studied equations like this for centuries. First really happened in good parts of India where we started solving equations like this. Amazing. So actually, I know there are solutions to this equation. I mean, one solution is A equals 2, B equals 1. In fact, you can see this. 4 minus 3 times 1 squared is indeed 1. Now I have to unravel that. So what's that saying? If A is 2 and B is 1, that means that alpha is 1 less. So alpha is actually 1 and beta is the same as B is 1. Which means that G is alpha plus beta over 2, 1 plus 1 equals 2. So G is actually 1. And R is alpha minus beta over 2 is 0, which is not a solution to the original problem. Okay, that's not very helpful. However, I need to know there's another solution to that one. Here it is. A equals 7, B equals 4. 49, it does indeed, if you take away 3 times 4 squared, 3 times 4 squared, 3 times 16, 48. 49, take away 48 is indeed 1. Which means alpha is 1 less 6, beta is the same as that. In which case, G is actually the average of this. G is 5, and R is the difference, divided by 2, R is actually 1. Bingo. That's the solution. If you have 5 green balls and 1 red ball in the bag, the probability of choosing 2 different balls being different colors is 1/3. It is. Double check it. In fact, here's another solution. A equals 26, B equals 15, in which case alpha is 1 less is 25, beta is still 15, and then G is the average of those, which is 20, and R is the difference. 10 divided by 2 is 5. Bingo, there's another solution. In fact, there's infinitely many solutions to this equation. They all correspond to distribution of green and red balls in a bag, giving that probability 1/3. This is amazing. So we've got to talk about that. Where am I getting these solutions from? What's going on here? Who is Pell? How did this Indian mathematician solve this stuff? What's happening here? How does it help? What's really going on here? What are all these solutions? All right, but I have to clean the board. Back in a moment. Throughout the centuries, mathematicians have been trying to solve all sorts of different types of counting problems, and they noticed that often these counting problems were reduced to a single equation like ours, something like a squared minus 3b squared equals 1. Now we've got the number 3 there, but actually that could change. They noticed that often come to an equation of the form, for some special number n, a squared minus n, b squared equals 1, I want counting numbers, I want numbers, integers bigger or equal to 1 that fit an equation like that. This came up a lot throughout the millennia. And people really worked hard to try to solve these equations. Now there's one special class of equations where these are actually particularly easy to solve, namely they have no solutions. If n itself turns out to be a square number, like n equals k squared, say, then this will have no solutions. Look, a squared minus k squared b squared equals 1 is really saying I've got one square number a squared equals a second square number kb squared, but off by 1. I'm looking for two square numbers that differ by 1. Well, there aren't any. There aren't any. I mean, here's the simplest square number, 1. The next square number would be 4, but I'm going to add this little L shape of dots around. I can see, well, they differ by 3, not differ by 1. The next square number would add 5 more dots to that picture, the next L shape. So I've got 1, 4, and 9 in that picture, and I can see, well, any two of those at least differ by more than 1. I can't get to just any two square numbers differing by 1. The next square number, up to 16, is going to add 7 more dots to the picture. So 16 differs from any other square number, but at least those dots there I just drew, 7. You can see there's going to be no two square numbers that differ by 1, except maybe the very extreme case where I have the square number of 1 squared and the square number of 0 squared. But I wanted to actually count things, no zeros. So this never has a solution. So people became fascinated, okay, square numbers here don't have solutions, but actually non-square numbers often do have solutions. In fact, non-square numbers have infinitely many solutions there. Our 3, when I had a 3 there, I was just pulling out solutions. These became very famous equations. Today they're known as PELL'S equations in the West, but the story to that name is somewhat strange and circuitous. For example, it's really probably Brahmagupta who really started playing with equations of this form in a very serious way and noticed many profound properties of numbers that satisfy equations of that form. He really got this work off the ground. That was some, 1,500 years ago. And in fact, it was so good his work that later, some 500 years later, Bhaskara back in India as well, saw that Brahmagupta's thinking actually led to a way to find all the solutions to those equations. So that Indian scholars knew how to solve these equations completely and utterly. Brilliant. Now the West was slow to catch on. It took another 500 years before European mathematicians saw a way to handle these solutions. Now a lot of people were doing work on that, Fermat and Wallace and so forth, but then the story about the name Pell is kind of like a little contorted. John Pell was an English mathematician. He actually was working to revise editions of translations of books. Turns out Johann Run wrote a book that was translated by Thomas Brankner for English readers, and John Pell was actually writing a revised edition of Thomas Brankner's translation of Johann Run's book. And in Johann Run's book, he described a method of solution to this equation by English mathematician William Brahmagupta. So we've got here an English mathematician writing a revised edition to an English translation of a German book that describes a method solution to this equation discovered by William Brahmagupta in Europe. Okay, great. So that was all very clear in then. I don't know if you got me then. But then later, Leonard Euler read John Pell's book and mistakenly thought that the solution that John Pell was describing in the revision of the translation of someone else's method was actually due to Pell. And Euler started calling it Pell's equation. And Euler, being such a famous mathematician, people just followed suit and of calling it Pell's equation to this day. Pell never claimed to solve this equation. He was actually translating other people's work about William Brahmagupta's solution to this equation. Okay, but it's Pell's equation. But actually, the solution goes back to those fabulous Indian scholars. All right, so then the question comes, right, how am I solving this equation? So mathematicians have been thinking about this all the time, and you saw me in the last section just pull out 3 or 4 solutions to that out of the air. Well, let me show you the general method how to generate solutions. It's going to be one of these annoying things, but I'll just show you the method and you're going to go, but why, but why, but why? I will not skimp on the mathematics. If you're still interested and want to know why the method I'm about to describe works, see the later video of this section of this video. I'm going to give everything. So here's how I was creating solutions to that particular version of PELL'S equation with the number 3 there. That's a non-square number. We had one solution. So you can see one solution. I can see that A equals 2, B equals 1 is pretty good. A equals 2, B equals 1 is grand. Now, here's pulling out of the air, but there's a good reason for it. I'll explain it all. I'm going to look at this number, 2 plus 1 copy of root 3. And then there's the 2 and there's the hidden 1. Now I'm going to square it, 2 plus root 3 squared. If I square it, I'll get 2 squared is 4 plus root 3 squared is 3, so I'll get a 7 plus 2 copies of this. So that's going to be 4 root 3 plus 4 root 3. I claim that 7 and the 4 represent another solution. A equals 7, B equals 4. So I think I did that one. 49 minus 3 times 16. 49 minus 48 is indeed 1. Now I'm going to do this cubed. I'll do this next power of this like fundamental solution, if you like. Cubed. Well, this is what it is squared. So it's really 7 plus 4 root 3. That's it squared times another one of these, 2 plus root 3. All right, okay, so let's assume I'm happy with my square root arithmetic. I'll get 14 plus 4 times root 3, 14 plus 12, that's 26. And the root 3, so I'll get 8 root 3s plus 7 root 3s makes 15 root 3s. I claim 26 and 15 are another solution. A equals 26, B equals 15 is another solution. Check it. 26 squared, take away 3 copies of 15 squared, differs by 1. Whoa! In fact, just for fun, I'll do it one more time. The next power, in fact, I claim all the powers of 2 plus root 3, I'm going to give all the solutions to this. So what I've got so far is 26 plus 15 root 3. That's the cubed times by another one. Here goes. Can I do this arithmetic on the board right now? 52 plus 15 times 3 plus 45. 52 plus 45, that's like 97 plus 30 root 3s and 26 root 3s plus 56 root 3s. I think I did that correctly, but I don't really know because arithmetic is not my forte. But I bet A equals 97, B equals 56 is yet another solution. I'm generating loads and loads of solutions to this. Why this is working? Well, of course I want to talk about that. We will absolutely do that. Okay, before I go, just for completeness, let's take our solutions that we had before to PELL'S equation and translate them back to actual counts of green and red balls in the bag. Just get this back in our heads. So here's the solution I wrote up moments ago, and I did one more power of 2 plus root 3 and I actually got that solution as well. All right, so if you recall, we had these intermediate numbers. We had alpha, I believe, was A, just 1 less, and beta was the same as B. And then to get the G and R's, we had the formulas G was going to be the average of alpha and beta, and R is actually their difference divided by 2. So there's how you translate back from the solutions to PELL'S equation back to the actual numbers for the count of balls in a bag. All right, so I think it's what I had earlier on in this video. I don't think I did this one. So alpha is indeed 1 less than A, beta is the same as B. So the number of green balls is the average of 96 and 56. I believe that's 76. And the number of red balls, their difference, 40 divided by 2 is 20. That's how we translate back. This one, alpha is 1 less than A, yep. Beta is the same as B, yep. G would be the average of those two numbers, too hard for my brain. R would be the difference of those two numbers, also too hard for my brain, divided by 2. But we can work it out, But of course, the real mystery is, the real interesting question here is, why do solutions to this correspond to powers of 2 plus root 3? Raise this to more and more powers. Each power corresponds to a solution. And in fact, that's all the solutions. That's really deep. Okay, do you want more? So far we've played with the probability of choosing 2 balls at random that are having different colors being 1/2. That was Dick Hess's original question. Then we played with the probability of choosing 2 balls having different colors being 1/3. We analysed that and got PELL'S equation, a squared minus 3b squared equals 1. So we kind of analysed that. Then, well, do you want to play? Because I think the next fraction that one wants to play with, if I've done 1/2 and 1/3, what if I do the other third that's missing, say 2/3? So let's make that the title of this section. The probability of the difference of getting two balls of different colors is now 2/3. What can we say about the original count of green balls and the original count of red balls in that bag, given that particular condition? All right, so I'm going to just follow the work we've been doing all along, see what the algorithm tells me. I'll let G be the number of green balls, I'll let R be the number of red balls. So I want this probability 2/3 to be choose a green followed by a red, G plus R minus 1, or choose a red followed by choosing a green, G plus R minus 1 again. There we go. That's the equation I have to play with this time. Again, it's just the same fraction repeated here, so I've really got two-thirds equals twice GR over G plus R minus 1. 2's cancel. All right, that's great. So I'm really saying this quantity, G plus R times G plus R minus 1 equals 3 GRs, 3 GRs. All right, so there's my equation. Fabulous. Okay, so last time I was very careful about when could G equals R. So let me just check here. Could G equals R? Could G equal R in this case? If that's happening, then I've got 2G's times 2G's minus 1 equals 3G squared. Okay, that's telling me 4G squareds minus 2G's is 3G squareds. That's telling me G squared equals 2G. G squared equals 2G. G is not 0, assuming you don't have a lack of balls, in which case G equals 2 is the solution. And G equals R, so R equals 2 is the solution. Oh, in this case there is a solution with our equal number of green and red balls. We have got one solution. G could be 2 and R could be 2. If you like, you can check. Got 2 green balls, 2 red balls in a bag. The probability of choosing 2 balls of different colors, I bet is now really is 2/3. Oh, that's interesting. All right, okay. So G could equals R. Otherwise, well, if G, I've got one case, G equals R, done, or G doesn't equal R. So either more green balls than red, or more red balls than green. What we call colors doesn't matter. So let's now assume, let's go for the case where the count of balls is different. Let's assume G is bigger than R. All right, okay. So now we have to analyze that. That's a nice little surprise. That was a surprise. Okay, but let's keep going. I'm going to do the same thing I did before. I'm just going to copy that work before. I let alpha be G plus R, and I let beta be that difference, G minus R. Because now I can say this equation is really saying alpha times alpha minus 1 equals 3. Now G is alpha plus beta over 2, and R is alpha minus beta over 2. Yes, G is bigger than R, so we're in that case. Yep, that's all good. We've got integers here. All right, so what's that telling me? That's telling me 4 alpha squares minus 4 alphas equals 3, that's alpha squared minus beta squared, so 3 alpha squared minus 3 beta squareds. So really, alpha squared minus 4 alpha equals, 4 squares minus 4 alpha, yep, equals negative 3 beta squareds. All right, it seems very compelling to add 4 to that, and hence 4 to that. So this is really saying alpha minus 2 squared equals negative 3 beta squareds. All right, so more room, don't need that right now. All right, following what I did before, it seems compelling to call that A. So let A now be alpha minus 2 and call that B, B beta, so it's just exactly the same as before. This is, oh, there's a plus 4, sorry, missing a plus 4. This is now saying A squared equals negative 3B squared plus 4. That is A squared plus 3B squareds equals 4. Ooh, okay. This is different. This is a different equation. Before we had a minus sign there and had this equals 1. Now we've got a plus sign here and it equals 4. This is interesting. I recognize that equation from my geometry classes. If these were x's and y's, x squared plus 3y squared equals 4. That's the equation of an ellipse. That's the equation of an ellipse. That if I let a and b be real numbers, I just draw the whole equation with an a-axis and a b-axis. If b is 0, a could be either 2 or negative 2. So it goes through 2 and negative 2. And if a is 0, B could be square root of 4/3 or negative square root of 4/3. I don't know, some numbers. 2 over root 3 or negative 2 over root 3. all the solutions, all the real number solutions lie on this, in which case, oh, I'm looking for integer solutions. There can only be a finite number of integer solutions, because here's zeros, ones, twos, and then all the integer points in between. Whoa, there can be at most a finite number of solutions, not an infinite number. And in fact, I wonder, we want A and B to be at least bigger than 1. So the question is, does this one work? It's probably the only one that's going to work next. Does A equals 1, B equals 1 work? Or maybe A equals 2, B equals 2? I don't, well, hang on, what works? What works? Well, do you know what? We know we're in a finite realm. You can actually check all the solutions. Now, I bet we can find, I think I can see another one. Can I see another one? Yes, I can see A equals 1, B equals 1 works. Look at that. A equals 1, B equals 1 adds up to 4. That means alpha was A plus 2. So alpha is 3 and beta is 1. So alpha is 3, beta equals 1, which means G is the average of these. G equals 2 and beta is their difference divided by 2. R is 1. There is another solution. Oh, bingo. G equals 2, R equals 1. We now have 2 solutions. And do you know what? I bet you can now just by inspection realize these are the only solutions. In this case, there's only 2 counts of green and red balls in bags to give this probability equaling 2/3. Whoa, completely different character. So how did we have infinitely many solutions before? Well, before we had the equation a squared minus 3b squared. A squared minus 3b squared equals 1. If I think about what that graph's like on an AB axis, that's a hyperbola. When b is 0, a could be 1 or negative 1. And when b equals, when a equals 0, well, never going to be. In fact, the graph would look like this. So it's possible that this graph could actually pass through infinitely many integer points, because this graph is actually kind of unbounded, and it turns out it does. It passes through infinitely many points to give us integer solutions for G and R, which is amazing, So that's the difference. So this case turned out to be hyperbolic, which allow for the potentiality of infinitely many solutions. This case is elliptical, whoa, which means, there's only going to be a finite number of solutions. Every integer solution has to be somewhere on that curve. Very different character, which then suggests a whole realm of research. Now maybe we want to play with the whole possibilities of P over Q, some reduced fraction P over Q. When will this lead to hyperbolic type situations and give us infinitely many solutions? When will this lead to elliptical type situations and give us only finitely many solutions? And, what's between an ellipse and a hyperbola? That would be a parabola. What's a parabolic solution to this? Whoa, how do I think about all this stuff? Well, this is the wonderful work of Robert Monod, who actually did work on this, and wrote a beautiful paper that came out very recently about it. So check out his reference if you want to play with it too. He's done some great thinking in this regard. I'm really impressed. It's beautiful stuff. And I love it all's inspired by a beautiful, beautiful problem from Dick Hess. So thank you, gentlemen, for actually playing with this gorgeous mathematics. Now our job is for me to explain the history of the mathematics of PELL'S equation, actually show you why powers of 2 plus root 3 really do give all the solutions to PELL'S equation that we want to play with in this infinite case. All right, if you're game, I'm going to do it. Okay, let's get into the mathematics of actually solving PELL'S equation and explaining those weird powers of 2 plus root 3 is doing. So here's the general PELL'S equation. A squared minus n, b squared equals 1. We want 2 counting numbers that fit that equation for a given value of n. In fact, for us, n was 3. We were actually trying to solve a squared minus 3b squared equals 1. Now the theory actually began with Brahmagupta. Brahmagupta had the biggest insight all that made everything fall into place, everyone else really. Brahmagupta realized something very strange. How he thought of this, I do not know, but here's what he realized. That if you take this quantity like this, a squared minus nb squared, so some numbers a and b with an n there, and take another number that form, c squared minus nd squared, multiply them together, you will actually get another number of the same form. You'll get something squared minus n something squared. You can fill in the pieces, and the pieces are AC and BD, AC and a BD plus a BD, but an extra n in there, so sorry, handwriting here, plus NBD, and then sort of like a cross version, AD plus a BC, AD plus a BC, no n in that term. Whoa, Brahmagupta, 6th century, figured that out. Now, how does that help us out? Because, okay, we're looking for solutions to a squared minus nb squared equals 1. So if a and b are two numbers that fit that equation equals 1, and c and d are another two numbers that fit that equation equaling 1, so I've got one solution, two solutions to that equation, then actually they would say, oh, this equals 1. This equals 1, which means, oh, this thing equals 1 times 1. It equals 1. This represents a third solution. We have then that AC plus NBD squared minus NAD plus BC squared equals 1. Oops, the squared there. Forgive me. Whoa. So you got one pair of numbers that fit this equation, a second pair of numbers that fit that equation, then you can generate a third one. And now you've got those two and those two, generate a fourth one. Now you've got another two, generate a fifth one, and so on. You can keep generating solutions. Brilliant. Fabulous. But let me be very clear how this works for our example. So let's take Brahmagupta's brilliant little equation here and apply it to this. So we need one solution, but we need two solutions. Okay, the first solution I can see right away. I can just see that A equals 2, B equals 1 works. Got one solution. Second solution. All right, you can see this for a long time, and I know I've done it multiple times in this video, but here's the sneaky thing. If I want a second solution, well, if I just use the same one again, I'll call it C is 2 and D equals 1. That would be sneaky. Use the same thing twice here. Does it give me a third solution? Well, let's find out. It should be A times C and B times D, but an extra n in there. For us, n is 3. So I should get AC is 4 plus 3 times 1 times 1. 4 plus 3 is 7 squared. Minus 3, that's our n. B squared is like the cross version, 2 times 1 plus 1 times 2, no n's, times 4 squared. So 49, take away 3 times 16, yes, is 1. 7, 4 is the next solution. So another solution is A equals 7, B equals 4. I guess I'm just running out of letters here, it doesn't matter. Oh, what if I do it again? Well, if I use these two now to get another solution, here goes. I get 2 times 7 is 14, 1 times 4 is 4, but actually I want an extra 3, I want an n in there, 3. So it's 14 plus 3 times 4 is 12, 14 plus 12 is 26 squared minus 3 times the cross version, 2 times 4 is 8, plus 1 times 7 is 7, 8 plus 7 is 15, 3 times 15 squared is another solution. And off we go. In fact, these are the numbers I was writing down before. Whoa, whoa. So actually what I really started doing was I did Brahmagupta's formula with A squared minus NB squared, but then I did the same thing again. I did A squared minus NB squared right there. Very sneaky of me. So I did squaring to get to this one. But then I actually multiplied by this one again. I did another one, A squared minus NB squared, applied to this answer. So what Brahmagupta's method is really doing here, what I'm actually doing here is I keep using this 2, 1 over again, applying it to the answers I've got. So really, this makes you say, oh, we should be looking at powers of A squared minus NB squared. Those powers are to the K. That's what's really going on what I was just doing. So that makes you think, all right, to solve PELL'S equation, there's something, the mathematics behind those powers. What is it about those powers that's making things work? So let's talk about that next. Okay, so now we're looking at the powers of A squared minus NB squared. But you can't help but look at that and think, well, it's kind of like a difference of two squares. I mean, I know n is not a square number, but we could write this as, if we really wanted to, A squared minus NB squared is A minus root NB times A plus root NB. I mean, let's just do that. Let's just do that. Because that means then, if I do something like Brahmagupta's work, A squared minus NB squared times C squared minus ND squared, I could really think of this as a product of two things times another product of two things. So this would really be, let me do the minus parts of everything first, A minus root NB and a C minus a root ND times the plus versions, A plus root NB, C plus root ND. Okay, my pen is running out. Don't run out on me right now. Okay, so then I've got the sort of the minus version of things multiplied together and the plus version of things multiplied together that then get multiplied together. I can do it. I'm going to actually write this out. This is AC, okay, AC, then, okay, this stuff is going to be root n times root n. So that's n times b times d with plus. So this is plus nbd. Then I'm going to get stuff with the root n's in it. I'll get a minus bc root n and a minus ad root n. So I really get a minus ad plus bc root n. There it is. That's what that is. Okay, now let's do the positive version of that. And actually, I can see I can get the same AC, I can get the same NBD, and actually it's going to be positive because I had a negative times negative here is positive, and positive times positive here is positive. This is actually exactly the same, AC plus NBD. And then for this stuff, the root n stuff, I'll get a positive BC root n and a positive AD root n. I get a positive version of that, AD plus BC root n. Oh, so I've actually got exactly the same numbers going on here. Okay, my pens are bad. Same number there, minus same number there, plus the same number there. So actually, it's of this difference of two squares form again. This really does equal, this difference of two squares, put it back together, AC plus NBD squared minus NAD plus BC squared. Which is actually Brahmagupta's formula. Actually, I guess I just proved Brahmagupta's formula. I did the algebra. There it is, Brahmagupta's formula. So that's kind of cool. So thinking of this as a difference of two squares can actually lead to some results. So that means, okay, if I actually want to do powers of this, I might want to then think about doing, okay, powers of this as really powers of this times powers of that. Because I have a feeling the structure of this piece informs the structure of that piece. We had like things matching up in exactly the same way. I bet this is going to be like half the work in some sense. So let me look at powers of these things and see how similar they are. All right, let me use a pen that I think is going to work for us. Let's try this one. All right, so let me just focus on, let me do the positive version first. That's probably easier for my brain. A plus root n b to some kth power. All right, so what does the binomial theorem say? It says I can do all of a to the k and none of that. I could do k minus one of those and one of those. I could do k minus two of those and two of those and so on. So this would be binomial theorem. K choose 0, do everything applied to the a, no powers of that. Plus k choose 1, do a to k minus 1 and one of these, so a b root n. Plus k choose 2, do a to the k minus 2 and then square this part, which would be b squared n, b squared n. I'm putting all the n stuff at the very end. I want to see the n's, what's going on there. Plus then we're up to k choose 3, which would be a to the k minus 3. Now cube this. Cubing this will give me a b cubed. I'll get an n and an extra root n. In fact, now I can see. Whenever I raise this part to an even power, I'll just get whole numbers n, lots of n stuff. But when I raise it to an odd power, I'm going to get all root n's appearing. So I can see right now, I won't bother writing it all out, that I'm really getting some actual number alpha, some integer alpha, plus some other integer, but a root n taking it all along. So a power of a plus root n to some power k gives me some integer plus another integer times root n. All right, so that's that thing. I have a feeling this is very similar structure. What happens if I change things to a minus sign? If I change this to a minus sign, how messy is it going to be? This doesn't erase very well, that bright yellow. It's good color, but it doesn't erase well. If I change this to a minus sign, okay, apply all the powering to A, fine, use none of that. That's fine, that's not changed. Now do one of these. So apply k choose 1, k minus 1 of these, and then apply b root n, but there's a minus sign involved. So actually, this becomes a minus sign. Hard to erase, but there it is, a minus sign. Then do this squared. Well, I get a k choose a to the k minus 2, this squared, plus or minus doesn't matter. If I'm squaring, it makes it positive, no change. But if I do this cubed here, I'll have an extra minus sign floating around, actually have a minus sign right there. Okay, you can see what's happening. Whenever I do an even power of this, plus minus doesn't matter, it's going to stay the same. But whenever I do an odd power of this, I'm actually going to get a change of a minus sign, minus sign, minus sign. So what's going to happen now is I'll get a minus sign attached to all the root n stuff. Interesting. This is great. This is great. So that means, if I say, look at the powers, this is hard to erase. Okay, it's going to be very messy. I don't like this brand of marker, that's why I'm not using it, even though it's so bright. Well, let's see. if I recognize a power of this, I work out that power and get it a alpha plus beta root n, then I actually know that power right away. We just saw it's the same structure, it'll just actually be alpha minus beta root n. So if I know that, I know that, and if I multiply them together, I then know that. I know everything. So actually, to work out the powers of this thing, it's actually practically easier to work with this, the powers of a plus root n, because once I've got those powers, I'm actually really doing powers of this, which is great because we know powers of that correspond to solutions to PELL'S equations. So that means powers of this must actually be connected to the solutions of PELL'S equation as well. Whoa, whoa! So let me do it. Let me do it with our example. Let me show you what happened. That's all theoretical right now. How does it actually work? So for our example, we had a squared minus 3b squared equals 1. And we had one fundamental solution. We had a equals 2, b equals 1. That's our first solution we can think of. In fact, you can probably argue this is probably the smallest solution in some sense. I know that a equals 1 and b equals 1 doesn't work. The best thing we can do is actually a equals 2, b equals 1. That's like this tiny solution that is like the most smallest solution you could possibly get. All right, so what's Brahmagupta's method? He says take that solution, 2 squared minus 3 times 1 squared. That equals 1. Great solution. But now we're going to think of this as actually 2 minus 1 root 3 times 2 plus 1 root 3. Now Brahmagupta's method says take powers of that and you'll get more and more solutions. But we're saying you actually take powers of this and this. In fact, just focus on the powers of that. That will actually then yield to everything we want. Well, let's check that. Let me take the first obvious power of this one, the simplest one. Let's just do squaring. Quickly square this, I'll get 4 plus a root 3 squared is 3 is 7. 7 plus 4 root 3. 7 plus 4 root 3. Okay, 7 and 4. Now without doing any work, because I know it has to be the case, if I did squaring of this other version of it, I must get basically the same answer. 4 and 7 being the key numbers, 7 minus 4 times root 3. Which means if I wanted to square this, I would actually be doing 2 squared minus 3 times 1 squared squared would actually be the product of this and this. What is this? Well, it'll be just, well actually I can see the difference of 2 squareds. It'll be 49 minus 3 times 16. Oh, it's actually 7 squared minus 3 times 4 squared. Yes, yes, that 7 and 4 really was the solution to PELL'S equation. Whoa! Whoa, that's it, that's it. So actually it says we can just focus on powers of 2 plus root 3 instead. They're actually easier to compute in practice. Do more and more powers and out come all the solutions, lots of solutions to PELL'S equation. The question is, are they all of them? Are we missing any? That's the next issue which we need to attend to. Okay, so it was actually the Indian mathematician Bhaskara who, looking at Brahmagupta's work, realized that Brahmagupta's thinking led to this astounding result, that actually Brahmagupta was on top of getting all possible solutions to equations of this form. So here's the result. Here's the astounding result. Suppose you happen to find one solution to this equation, like a simple one, like we did. We had a equals 2 and b equals 1. For our version, a squared minus 3, b squared equals 1. Okay, you might be able to find a solution. Suppose you found one. And then let alpha be a plus root nb. Let alpha be that particular part of that difference of 2 squares formula, just like we were doing. Let's assume alpha is the smallest value possible. Now what do I mean by that? What do I mean by that? So we've got a pair of numbers a and b that fit this equation. They're both counting numbers, they're each bigger than or equal to 1. Okay, that's grand. And then let alpha be a number like this. In fact, alpha is going to be some positive integer bigger or equal to 1, root n integer bigger or equal to 1. So there's a number bigger than or equal to 1 right there. Well, bigger than 1 actually, strictly bigger than 1. Oh, that means, okay, you've got some value a and you've got some value b. This has some value. But you can check, are there any smaller values of a and any smaller values of b is what I've got? Is there anything underneath that that's also a solution? So if you've got one solution, you can actually hunt down for all smaller values of a and b that might be solutions as well. That's a finite list you've got there. You could work on that. Check. Check there are no smaller solutions under the one you happen to get. Okay, so that's what I mean by smallest. You've got one solution, check for all the a's and b's that could be smaller, make sure they're not solutions as well. If so, they go with the smaller one still. Great, choose the smallest one possible. That's what I mean by smallest. All right, so choose the smallest value you can, get one solution, then you can find a smaller solution, use it. Then the claim is, every other solution to this equation is actually given by a power of that smallest solution. Those powers of that smallest solution give every possible solution and doesn't miss any. So this equation has infinitely many solutions and it's given by powers of the smallest solution. Just find one solution, you've got infinitely many, in fact you've got them all. That is amazing. So my job now is to prove that. I'm going to prove that right now. So let's do it. We can do it. All right, it's going to be a little bit, intellectually meaty, but that's all good. We're out for it. It's only been about 50 minutes for this video. Why don't I have another 20 minutes? We'll see how this goes. All right. So let's see. So let's assume we have a pair of integers a and b that solve this equation. And I'll follow this notation, let alpha be a plus root n b, knowing that a squared minus n b squared equals 1. All right, that's great. Alpha is definitely bigger than 1. We noted that already. A is bigger than 1, bigger than equal to 1, b is bigger than equal to 1, so this is definitely larger than 1. It's a positive number bigger than 1. Actually, if I do the difference of two squares formula, what I've got, I do know then that a minus root nb times a plus root nb equals 1. There's my alpha, that's alpha. So actually that tells me I have a formula for a minus root nb. A minus root nb is 1 over alpha. All right, don't know if that's handy, but I'm just trying to gather as much as I can right now. All right, that's great. Alpha is bigger than 1, therefore 1 over alpha is a number less than 1. All right, alpha is positive, therefore 1 over alpha is also positive. This is actually between 0 and 1. Okay, there's a bit funky notation right there, but I know that 1 over alpha is between 0 and 1 is actually given by a minus root nb. All right, handy, maybe. I don't know. Okay, we'll see. Just playing. Okay, so this is the smallest possible solution. Now, the claim is that any other solution to this equation must be given by powers of alpha. So let's suppose we have another solution. Suppose xy is another solution to the equations. That means it must fit this equation. X squared minus n y squared equals 1. Okay, to have a better pen because I don't want this to run out today. All right, so there's another solution. I guess I want to do a similar sort of version to that. So maybe I'll let beta be the corresponding version of that. Oh, my pens are just not good today. All right, so let beta be that. The claim is that the claim is that this beta corresponding to the solution must be a power of alpha, must be coming from this form. We have to prove that this beta is really some power of that alpha. That's what it means to be this to be a matching solution from this difference of squares stuff. All right, so we have to prove beta is a power of alpha. Okay, let me think of it this way. Let's choose a pen. I know it's going to work. I just can't erase it well. Let's see what happens. All right, I've definitely got lots of powers of alpha. I've got 1, then I've got an alpha, and I've got an alpha squared, and alpha cubed, and so on. I've got an alpha k minus 1, an alpha k, and an alpha k plus 1, and so on. So on the number line are all these powers of alpha. And I want to show that beta is actually one of those. Maybe it's that one, maybe it's that one, maybe it's this one over here, maybe it's this one, maybe it is that one, maybe it is alpha. Okay, I want to show that beta actually matches one of these points on the number line. Let's be naughty. Let's see what happens if it doesn't. Let's assume beta actually misses, actually lands in between two powers of alpha. So let's assume that we have alpha to the k is less than beta is less than alpha to the k plus 1. It's strictly between two powers. It misses powers. Then, according to the result, that can't happen. Something has to go wrong. That cannot be true. We have to show that if we play with this assumption, something's going to go wrong. So what goes wrong believing that? All right, what could go wrong believing that? Well, okay. Well, let's see. I'm going to divide this by, well, I kind of want to divide by alpha to the k, but I'm a little bit nervous about doing something big. What if I divide by just a single alpha? Because that would actually take me from this range to this range. Alpha to k minus 1 is less than beta over alpha is less than alpha to the k. That gives me a number in this range. I wonder if that corresponds to a solution as well. If I've got one solution between there, that means I have a solution in there. If that's true, I could do it again, have a solution there, solution there, solution there. I could have solutions in between each of these powers of alpha. And that feels troublesome. But before I think through the logical consequence of that, let me check. Could beta divided by alpha be another solution? All right, I'm going to get rid of this astounding result if I can erase it. Oh, hard work. These pens are not good. All right. All right, you have to watch me groan here and wobble the board and make lots of annoying noises about this particular pen brand. All right, so what goes wrong? Oh, sorry, what is it? Could it be true that that's also a solution? So I need to work out beta divided by alpha, and do you know what? I can. Beta divided by alpha is beta, I know what that is, beta times 1 over alpha, and I know what that is. This is x plus root n y times, and 1 over alpha is a minus root n b. Let me actually work that out. This is actually a times x minus n by, minus n by. Now I'm going to get some root n stuff. I'll get minus, let's see, what do we get? Or plus ay root n minus bx root n. So ay minus bx root n. All right. Now, it's just like Brahmagupta's form. There's a little bit of variation with these extra minus signs around, but I do know that a squared minus nb squared equals 1. I do know that x squared minus ny squared equals 1. I bet you can now prove that this thing, ax minus nby squared minus n ay minus bx squared also equals 1. In fact, it's the same algebra as Brahmagupta's formula. It does equal 1. It follows from the product of these two. Whoa, check it out. Which means, oh, this really is corresponding to solution to my original equation. Something squared minus n times something squared equals 1. Beautiful, amazing, astounding. So now I can see what's going to go logically wrong. Let me get rid of that, because I might need the space before it dries too hard and makes it impossible to erase. We now have, given a solution here that's in between, there's a beta, I can now get a solution that's between the next lower pair of powers of alpha. Then divide by another alpha, same work, then I'll have, another number between a pair of powers of alpha. I keep getting solutions between these pairs of powers. In fact, I'll get solutions. Here's my 1 alpha squared, alpha cubed. I'll get a solution in there. I'll get a solution in there. I'll get a solution in there. Strictly between 1 and alpha. But you know what? We said, let's make sure alpha is the smallest solution. There is no solution between 1 and alpha. Make sure you got the smallest one. Which means, if any solution lands between a pair of powers, that means, contradiction. We've got a smaller solution than what we said. That cannot be happening. This cannot be happening. It cannot be happening that beta, any other solutions between a pair of powers of alpha, it must be that beta is a power of alpha. Whoa! Every solution to PELL'S equation is a power of the smallest solution you can find. Wow. Now, of course, the hard part now is to actually make sure, how do you find even one solution? Because once you've got one solution, then you can do that work to make sure you got the smallest one, get the smallest one, and once you've got the smallest one, then you've got all the solutions. Next challenge is, how do you find just one solution? Does every version of PELL'S equation actually have a solution? Well, that's actually very, very tricky stuff. That's worthy of another video someday, or just Google it. How do you find what people call the fundamental solution to PELL'S equation? And there's another story that just unravels. Wow, you've got to love mathematics. The more you think about it, the more it just unravels and becomes deeper and deeper and deeper, and just, it's glorious. What can I say? Math is just wondrous. So thanks so much for hanging in there. If you watched all 70,000 minutes of this video, I'm impressed. So thanks so much.